All right, so welcome everyone to CS 364B. It's a class called Topics in Algorithmic Game Theory. It's a class which is not taught all that often. It's probably been about 5 years since I've had the opportunity to do it. So this is about advanced topics on the interface of computer science and economics. So quick poll. So who in the room has not taken 364A last quarter at some other time? One. Any others? Two. Okay. So what's your guys' background? Like, do you have any experience with, are you from CS or for econ or?
I'm from stats.
You're from stats.
I read through quite all the notes over the holidays though.
You read through all the notes over the holidays? Okay. I hope you did other things too over the holidays. How about you?
I did CS as an undergrad. I'm working with semester hard here.
Okay.
I've gotten into econ.
Okay. Okay, so cool. So, I mean, the good news, you know, I'm not going to, I realize it's, I'm basically going to give the lectures more or less assuming that you did take 364A. You know, I realize a lot of that stuff has been, you know, a few months ago, which is a long time given all the classes that you've taken. I realize there's going to be rusty stuff. I'll take that into account. The good news, if you're really rusty or if you never took it all, is there's a full archive actually from last quarter's class. So there's full lectures on YouTube. And I finished all the lecture notes for all 20 of the lectures. And I'll try to remind you, hopefully most, if not all of you, got the email I sent out Monday. So I'm going to try to, before every lecture, just say, you know, what you might want to spend 20 minutes reviewing before class, just to make it a little easier to follow what I say in real time. Okay? So the plan for 364B, pretty much the whole quarter, we're going to discuss aspects of mechanism design. And you know, this is an advanced class, so the focus is really going to be to try to be on cutting edge stuff. Okay, so lots of stuff in particular, really just from the last 5 years. I mean, the whole field of algorithmic game theory is only about 15 years old. Most of what we covered in the fall was within the last 15 years, but today, or not today, but this quarter, it'll really just even be the last 5 years. So what's mechanism design? So when I introduced this, I called this the science of rulemaking. You might remember the original sort of story I gave you about Olympic badminton, and then we proceeded to talk about lots of different applications, especially auctions. And just to remind you, the high-level goal in mechanism design is you want to design systems where you have strategic participants. Okay, so they're users of your system, and they're autonomous. They can do whatever they want. And in general, their objective is different than yours. Okay, so for example, we're going to be talking a lot about auctions. And as an auctioneer, maybe you want an efficient allocation of resources, or maybe you want high revenue. That's not what the participants want. Right? They want to maximize the net utility they themselves get out of the auction. So there's a conflict there. And despite that, despite the fact you have these participants that are autonomous with different objectives than yours, you want your systems to have good performance guarantees. Okay? Perhaps high welfare, perhaps high revenue. We'll talk about a couple different examples. So that's the high level of mechanism design. Let me jog your memory with a specific case that we already understand well, and then we'll quickly move on to things that we don't understand so well yet. So scenario one of the 3 that we'll discuss today. Oh, by the way, so the lecture format. So I'm going to give one lecture, which is roughly ballpark 75 minutes. Then we'll have a 10 to 15 minute break. And then there'll be a second lecture, which again will be ballpark 75 minutes or so. Okay, that's the plan for today and for the rest of the weeks. So we should wrap up by about 5 every Wednesday. Okay, so the first of the 3 scenarios we'll talk about today. Let's assume that there's k identical goods. So maybe someone's unloading a bunch of old black iPhone 4Ss, something like that. So not worth that much these days, probably. And you can go ahead and think about k equals 1. What I'll say will be interesting even when k equals 1, single item auction. And each bidder wants only one of these. And it's important you know the terminology for this. This is called unit demand. Okay? So a bidder has unit demand preferences if they really only want one of the goods that's available for sale. And each bidder has a private valuation V sub I. V sub I is the maximum that bidder I would be willing to pay for one of these items. By private, I mean that is known to this bidder, but it is unknown both to the seller and to the rest of the bidders, the other n-1 bidders. Okay? And we want to think about the interesting case where the number of bidders n is bigger than the number of goods k. Okay, so how do you solve this problem? Okay, well, what do we want? So if we're interested in maximizing the social surplus, which is the objective function that we're going to be discussing today and for a couple of weeks, then we use a variant of the second price auction, of the Vickrey auction, which I'll call the Vickrey auction. Okay, so this is something you saw last quarter. So the Vickrey auction is what's called a direct revelation mechanism, which means the very first thing you do is you're like, look, bidder, I don't know what you want. I don't know what your private valuation is. So tell me. You collect this information in the form of bids. So one per bidder. Again, bidders are autonomous. They don't have to tell you what they want. So they're just going to submit some bid BI to maximize their own objective. Then in a direct revelation mechanism, there's an allocation rule and there's a payment rule. Remember, the fundamental decisions are who wins in your auction and what do they pay. So the allocation rule says, given the bids expressed by the bidders, who wins? And so here we just pick the top k bidders. So give the goods to the k highest bidders. What should the winners pay? Well, remember in the single item auction, k equals 1. The Vickrey auction, for incentive reasons, we looked at the second highest bid. When there's k copies of an item, analogously, we use the k plus 1th highest bid. So if there's 10 items, we use the 11th highest bid, the highest bid of a losing bidder. Okay? So charge all winners the k plus 1th highest bid. So that's what I'm going to call the Vickrey auction. Let me remind you the basic properties of the Vickrey auction and why we like it. In fact, in the fall, we deemed this an awesome auction. So why did we call it that? Well, so it has good incentive properties, it has good performance properties, and it has good tractability properties. Okay. So by incentive properties, the formal term, it's a bit of a mouthful. So dominant strategy instead of compatible, or DSIC for short. And so the main condition here is that revealing your private information, that is setting your bid BI to your private valuation V sub I, is a dominant strategy, a foolproof strategy. Remember, that means it maximizes your utility, so the value you get for the good if you win it minus the price that you pay. It maximizes your utility no matter what the other bidders do. So it frees you from having to reason about what the other bidders want and how they behave. You don't care. You know your best response no matter what. So truthful bidding, a dominant strategy, meaning it's guaranteed to maximize, among other things, the quasi-linear utility. So remember, this is your value for the good if you get it. This is the notation I'm using for the allocation rule, x sub I of the bid vector B. So this is 1 if bidder I is a winner, that is if it's in the top k bidders, 0 otherwise, and then we subtract out what it has to pay. Okay, which is 0 if it loses, or the k plus 1th highest bid if it wins. So this is a property we proved last quarter. I'm not going to prove it again now. And then the other part, which we don't mention as much because we almost always have it, is what's called individual rationality, which is that truthful bidding also guarantees non-negative utility. Okay? And the reason you're guaranteed non-negative utility with a truthful bid is that the price that you charge a winner is always at most the bid of that winner. Right? So you take the people with the k highest bids and you charge them all the k plus 1th highest bid, so you charge them less than their own bid. So if the bid is truthful, then this quantity is non-negative. So those are the incentive guarantees of the Vickrey auction. So that's number one. So what are the performance guarantees? So if what you want is an economically efficient allocation of resources, meaning you want to maximize the surplus, then even though you didn't know what people wanted in advance, even though the seller had no knowledge of these valuations, this is something you get after the fact, assuming bidders bid truthfully, as they are incentivized to do. So the Vickrey auction maximizes the surplus. I'll also probably sometimes call the surplus the welfare, which in this context is just the sum of the bidders of their value for the good if they get it. And this is assuming truthful bids, of course. So because you only have k copies of the item, you can only set k of the x sub I is equal to 1. And if you want to make this as big as possible, of course, what you should do is give it to the ones with the biggest VIs. If the bids, the BIs equal the Vs, the VIs, well, then that's exactly what the Vickrey auction is going to do. Okay? So that's the second thing. And then the third thing is that it's a simple / tractable auction. Okay, and I'm going to be pretty vague for the first couple of weeks about what a simple auction is. This, for any definition of simple you can think of, this pretty much qualifies. Certainly it's polynomial time. Okay? So polynomial time and simple. Okay? So looking ahead, what we're going to talk about for at least the first half of the class, maybe even a little bit more, is to what extent can we get all three of these properties more generally, okay, for more general settings that we might want to solve. And so we're going to start with a couple weeks about the happy special cases, although still much more general than scenario number 1, where we can just get all of these things. Okay? We can get all the incentive guarantees we want, all of the performance guarantees we want, and all the tractability guarantees that we want. And there are a number of interesting cases, and the theory is very nice. Then we'll move on to cases where we'll be able to prove you cannot get all three of these, or at least not this strong a version of all three of these types of guarantees. And we'll spend some time exploring the various compromises and trade-offs between them. Okay? So at a high level, that's what the first roughly half of the class is going to be about. So any questions at this point? What I've said so far, I hope, is review for you. Now I want to move on to things which are not difficult, but which we didn't talk about explicitly, only alluded to in the fall. Okay. So what I want to talk about next, and what's going to be our obsession today and next week, are ascending implementations. And so rather than try to give you a formal definition, let me just show you what I mean by an ascending implementation for this particular problem, for scenario number 1. Then we'll take a step back with that concrete example and say, why might we care about this? And then we'll ask, what would a theory of ascending implementations look like? Those are the next few things we're going to do. All right, so for this special case of scenario 1, where you just have identical goods, again, think of k equal 1 if you want, and unit demand bidders, the ascending implementation is just going to be the familiar, what's called the English auction. Okay, this is what you would have seen in the movies, or I got to see an art auction at Christie's last year when I was on sabbatical in New York, and that's what they still use at those auction houses. And so here, you don't have people writing down bids in envelopes and submitting sealed envelopes, sealed bids. Rather, you have an auctioneer, and there's some item being sold, and the price starts very low, and lots of people want it at this low bargain price, but then they keep raising the price. And at some point, there's only one person left. Okay, at that point, this ascending auction concludes, and that's the winner. And the price is just the number at which the second to last bidder dropped out. Let me write down that a little bit more formally. So initialize the selling price to be 0. And we're going to have an initial set of active bidders. Okay, and initially, S naught, the active bidders, is just everybody. And what we want to do is we want to increase the price until supply equals demand. Okay? So supply, by definition, is just k copies of the good. And we want to get the price just right in the sweet spot so that there's exactly k people interested in buying the good at a particular price. Okay? So we run in rounds, as many as we need. And in each round, we identify the new set of active bidders, and this will be a subset of the bidders that were active last round. Okay? So for everybody who was active last round, we just say, well, would you still be interested in purchasing one of these goods at a price which was epsilon higher? Okay. So we define the bid S sub t, the active bidders at time t, to be the active bidders at time t minus 1, who, when we now ask them explicitly, say, yes, sir, I would continue to like a good at the price p plus epsilon. Okay? So here epsilon is just some increment that we fixed at the beginning of the auction. Okay? So it's some small percentage of the value that you're expecting to sell your good at. Okay? A penny, $1, $100, depending on the good. Okay, and so again, when I say claim to want, I really mean we explicitly ask all the bidders of S sub t minus 1. Okay, and we ask each of them a yes/no question. We say, do you want it at this price or not? And they give us the answers. Okay, and ST is the bidders who said yes, they still want it. Now, an invariant of this auction is we're going to maintain the fact that the demand exceeds the supply, and at the first time that the demand does not exceed the supply, we stop. So if this is the first such iteration, that is, if the number of bidders who now say they're interested at price p plus epsilon drops to the supplier below, k at most, then we halt the auction. Okay? So we need to choose the winners and we need to choose the selling price. So certainly everybody in S sub t wins. So we sell goods to everybody in S sub t. We sell it at price p, not at price p plus epsilon, okay, in the spirit of a second price auction. Okay. Now, it's possible a bunch of people dropped out in the last round. Even when k equal 1, it's possible that you had two active bidders. You asked them both if they were interested in p plus epsilon, and they both said no, and they both dropped out. Okay? So in that case, we're just going to give the residual goods, so the k minus cardinality of S sub t goods, to people who dropped out who were still there last round in ST minus 1, arbitrarily, either at random or according to some a priori fixed rule. It's not going to matter. Okay? So, and leftover goods, of which there are k minus the number of active bidders at the end, to arbitrary subset of the bidders who just dropped out. Okay.
At the same price P.
Thank you, at the same price P. Okay. And last iteration, when we asked them if they would be happy to have it at price P, they said yes. That's why they made it into ST minus 1. They were not willing to accept it at price P plus epsilon. That's why they're not in S sub t. But they did say they were happy to have it at price P, and that's what we give it to them at. Thank you. Okay, and then if that's not the case, if the demand is still too high, then of course we increase the price and start over. Okay. So there's many, many sort of variants of this ascending auction. And when you're doing this very simple scenario 1, the variants don't differ that much. So for example, one thing that I defined is that if you ever drop out of this auction, I never allow you back, right? So that's because I define S sub t to be a subset of ST minus 1. So if you ever say no, you can't say yes later. Okay? The auctions at, for example, Christie's are not like that. Okay? You can leave the room, walk around the block, come back, and if the auction's still going, you can re-enter. Okay? No problem. Right? But again, for this simple scenario, these variations don't make a big deal. Okay? For other more complex settings that we'll study later, they can matter. Okay, so this is what I mean by an ascending implementation. Okay, here's an example. Now let me give you some motivation. I took a problem, simple, but real problem, selling off k goods when you have more than n people interested. I gave you what seemed like a perfect solution. Okay, the k Vickrey Auction, people write down these bids, top k bidders, et cetera, et cetera, et cetera. We get all these great properties. Now, for some reason, I'm giving you another solution to the same problem. Okay, why am I doing that? Given that we have the Vickrey auction, why should we bother thinking about an ascending implementation? What possible benefit might there be? Yeah.
There are considerations we don't have in the model. So for example, bidders might have privacy concerns. They don't want you to know their true valuation or how much surplus they're getting. And they reveal less information in the ascending implementation.
Good. That's definitely one reason. Yeah. Yeah.
Do we want to look at a more general kind of problem? So rather than identical goods, because maybe design this option to deal with non-identical goods, kind of ascending implementation.
Also a good point. Yeah.
It's also no worse. It's the same thing essentially, which I guess we'll show, but you know, if we're any worse, then those considerations may not be valid.
Good point. Yeah.
It might be easier to get the bids in as opposed to having to get in all these pieces of paper where, you know, here are all the different bids. Here it's just, you know, if it's like you just wait until there's just one person left. So if there was a ton of bidders, I'm just thinking of like the combinatorial.
Simpler logistics. Oh, you're saying the communication.
Yeah,
Yeah.
like I remember you said in the combinatorial, just getting the bids itself, since there were so many different packages, was problematic.
Yep.
So more dramatic.
More dramatic. Good. I agree. I agree. Yeah.
Even though we're assuming people are very rational, it might be worth considering things like someone coming back after walking around the block and this getting more money for you out of the auction if they join again.
Good. Yep.
The bidders can't be sure of the exact valuation which they have, so it might vary a little bit. So this way, they might still be in the auction even if it's crossing the valuation.
Good. Yep.
It's older, so people thought of it first.
That's true. They've been doing these a lot longer. They've had ample time to switch, but you're right, inertia could be part of it. That's true. Yeah.
It's a more transparent process. Like, you don't have to trust anyone to collect all the bids.
Great.
It allows people to update their valuation if that sort of depends on what other people are doing.
Good point. Good point. All right. Great. Those all sound like excellent reasons. Let me maybe summarize a few of them, or sort of group / summarize a few of them. I can break the. We also break the problem into two parts. The first would be, if really all you cared about was scenario 1, is there any reason to do this? And some of the comments were more of the form. Some comments were the form yes, and some comments were the form looking forward. We can really imagine why ascending implementations might be especially useful. And I think both sets of comments are good ones. So let's just start with what about just with scenario 1 itself? So one reason was easier for bidders. And so notice that this auction is not a direct revelation mechanism, right? A direct revelation mechanism, by definition, what you do is you ask people for their private information. At no point does this auction ask you, what is your valuation? It asks you only a sequence of yes/no questions. Do you want a good at a certain price or not? Okay. Now, of course, this reveals people's valuations if you look at when they drop out, but at no point does a bidder actually have to do that cognitive task. Okay? So some of the comments were of that type. Other comments were of the form, sort of had to do with trust / privacy issues. So let's just say better on trust privacy axes. So what I mean by privacy, I'm not going to define it formally, but at the very least, you realize that if you win in an English auction in the ascending implementation, nobody, including the auctioneer, learns what your valuation was. They learn a lower bound on it in the form of the second highest bid, but that's all. Okay? In a sealed bid auction, possibly none of the other bidders learn the valuation of the highest bidder, but at the very least, the auctioneer does. Okay? And then the other thing mentioned was transparency. Right? So somehow if you see these prices going up and you see the bidding process and you wind up winning the good at a high price, it's sort of much more transparent to you why that happened, perhaps. Okay? Good. And then another one, potentially more revenue. So the comment about being more dramatic, I kind of put in this category. If you think about bidding wars, but in many different contexts, arguably you can imagine that might get you more revenue in an ascending implementation, and it wouldn't happen in a sealed bid format. So there's empirical work on this, and there's actually some supporting theory about why this would be true as well, although I doubt I'll have time to talk about it this quarter. Okay? And then, let's say, price discovery, et cetera, with non-identical goods. So this is something we had a long discussion about in the context of commercial auctions for spectrum licenses last quarter, which is, if you have, say, a lot of licenses up for sale, different geographic regions, different frequencies, you have your guess going to the auction about what your competitors want, but it's based on imperfect information. And so it's very common, you'll find out you thought there'd be, a bargain to be had here, and it turns out to be highly competitive, and vice versa somewhere else. So with ascending auctions, there's this opportunity for mid-course corrections. There's an opportunity for the different bidders to sort of coordinate and realize, some people to get out of each other's way if it turns out they're competing for something when something else would be just as good. Okay? So let's just say price discovery and flexibility, et cetera, once you pass to non-identical goods. Okay? Oh, and then someone else mentioned it's no worse, which was an interesting comment. In fact, the next thing we're going to do is formalize the sense in which this may or may not be no worse than the direct revelation auction. That's an interesting thing to think a little bit about. Okay, so does that, I think, summarizes the spirit of all of the excellent comments? Cool. I think I just got more participation in the first 30 minutes of this class than in the entire quarter last quarter, so, which is awesome. Don't get me wrong. Good. So certainly, all of these reasons and the fact that these are deployed widely in practice suggests that it would be really, it's very well motivated to try to develop a theory of good ascending auctions, ascending implementations. And that's going to be the goal of this week and of next week. Okay, that's pretty much the first major topic of the class. Okay. Questions? Can everyone see this board? Okay. Okay. All right, so what I want to do next, I want to stay just in the simple scenario number one for a little bit. And I want to make precise the assertion that the English auction is no worse than the Vickrey auction, okay, for scenario one. So what does that really mean? So let's start. The most interesting thing to think about is the incentive guarantee. So what's the incentive guarantee for the Vickrey auction or for a direct revelation mechanism? Dominant strategy incentive compatible. Truthful bidding is what people do. Right? That's essentially what this says. Right? So let's think about what the analog of truthful bidding is in the English auction. Right? Because again, this is not direct revelation. We never actually ask people for a bid per se. We don't ask people for their private information. So it's intuitive, but let me just give it a formal definition. So I'm going to call it sincere bidding. It's basically the same as truthful, but I'm going to try to reserve truthful for direct revelation mechanisms and use sincere for these iterative mechanisms. Okay, so sincere bidding just means that all queries by auctioneer are answered honestly. And so this will make sense in kind of all of the auctions that we study, but in particular in the current auction, this just means that when you're asked, do you want a good at a price of P plus epsilon, you answer yes, if and only if your valuation is at least P plus epsilon. Okay? That's what sincere bidding means over here. Okay? All right, so I'm going to leave this as an exercise because the proof is pretty much the same as the proof of truthfulness of the Vickrey auction. Oh, by the way, I'll talk about exercise sets at the end of this first lecture, but there is an exercise set posted. More on that later. So in this English auction, sincere bidding is a dominant strategy. Well, almost, up to epsilon. Okay. So the formal statement's on the exercise set, but it's what you'd think it would be. No matter what the other n-1 players do, You cannot improve over sincere bidding with any strategy at all, any action at all, by more than an epsilon. The epsilon comes in because there is a discretization error in this auction. Okay? So you might be able to get lucky and lie and stick in the auction one extra iteration. Okay? You don't actually want it at P plus epsilon, but you say you'll take it. If the auction happens to halt, you'll actually get the good at a price of P. Okay? So if your valuation is between P and P plus epsilon, you might want to stay in one extra round. But the claim is that's all you can do. All you can do is gain that epsilon. Okay? And again, so the idea of the proof is the same as in the Vickrey auction. So, how can you deviate in this English auction? What else could you do other than sincere bidding? Well, you're asked these yes/no questions, and you could answer yes when it's no, or vice versa, right? So if you answer no when the right answer is yes, that's dropping out early. That's like underbidding in a Vickrey auction, doesn't help. Or you can answer yes when it's no, which means you stick in longer, which is basically like up to epsilon, like overbidding in a Vickrey auction, which we also know can't help you. Okay, so that's the idea of the proof. As we'll see, this sounds trivial, I'm sure, right now. We'll appreciate this dominant strategy property of the English auction quite a bit more very, very soon, actually. Okay, and so in particular, as epsilon goes to 0, so if you imagine some kind of continuous ascending process in the English auction, then this really becomes a dominant strategy as the epsilon goes to 0. Okay. All right, and the one thing I do want to point out, which again you'll appreciate more and more as we go through this lecture, a difference between direct mechanisms and indirect mechanisms is that the action space for a bidder in an indirect mechanism is generally much, much richer than in a direct revelation mechanism. Okay? So in a direct revelation mechanism, your action set, the stuff you can do, all you can do is report a bid once. You have one chance to interact with this auction, okay? And it's right up front. Iterative auctions, you can in particular examine the history of what's happened in the auction so far. Okay? So I can look at what happened in the first 10 iterations, and if I want to, as a function of what's happened, make my decision in iteration number 11. Now, it's still the case that even though you have a richer action set, it's still the case in the English auction that sincere bidding is a dominant strategy. Okay? But that's why it's not a totally non-trivial state. Okay? So again, we'll develop this as we go along. But just note/warning, action set in indirect auctions much richer than indirect. Well, let me just say than direct to avoid parsing problems. And the main reason is you can have history dependence. Okay, so I want to plant that seed right now. Okay. All right. And as we'll see, this does matter very soon. All right. So what we're doing is we're trying to say that the English auction is just as good as the Vickrey auction. And we've said that for the incentive guarantee. Okay? Honest behavior is dominant strategy either way. So that's great, just as good. It's also true that the performance guarantee is just as good up to the discretization error. So again, this is straightforward, so I'll leave it as an exercise. So over here for the Vickrey auction, we say assuming truthful bidding, you get maximum surplus. So over here we say assuming sincere bidding, we get maximum surplus as epsilon goes to 0. So formally, assuming sincere bidding, English auction maximizes surplus up to k times epsilon error. So again, because of discretization, you might wind up giving goods to with value that have epsilon less than other bidders that should have gotten it instead. That can only hurt you by epsilon times the number of goods k. Okay. As far as simplicity, it's also clear it's a simple auction, and it's clear it'll terminate because the price goes up by epsilon every time. Once that hits the maximum valuation, obviously nobody else is. Under sincere bidding, no one's going to stick around in the auction. Okay. So someone made the astute comment that the English auction is just as good as the Vickrey auction, and this is the formal sense in which that's true. Okay. All right, so that's what I wanted to say about scenario 1. And now I want to slowly ramp up the complexity of the scenarios and see how our goals are going to change. Right? So any questions before we move on to scenario 2? So scenario 2 will be incomparable scenario 1. It'll also be very simple. So we definitely want to, as people have alluded to, we definitely want to start thinking about non-identical items. Okay, so identical items are also interesting. So all of our sponsored search discussion last quarter, for example, involved identical items. But non-identical items have lots of motivations. The original motivation for combinatorial auctions was auctioning off takeoff and landing slots at airports. And so obviously, those are goods that vary depending on the airport, depending on the time of day, and depending on whether it's takeoff or landing. We had an entire lecture last quarter about spectrum auctions, where the different licenses, while sometimes similar, are not identical goods. They vary in geography, they vary in the frequency band, and so on. Another thing about combinatorial auctions is sometimes people need to buy a distribution route. So you have some product and you want to distribute it all over the country. And so you need to contract with trucking companies and boat companies and so on. Travel agents need to put together, airfare and hotels and tours and so on. So all of these are reasons why, there's been a lot of theory thinking about non-identical items. Okay, so this is going to be a set U of M items. Okay, generally distinct. So that's obviously more complicated than scenario number 1. But here's going to be something very simple about scenario number 2. Okay, so in our first baby step with non-identical items, we're going to look at what are called additive valuations. Okay, and what that means is that each bidder I has a private value, willingness to pay, for each good J. Okay. So if I just give you J, your value is Vij. If I give you a bunch of items, your value for the bundle is just the sum of these Vij's for the goods J in the bundle. Okay. So the value of a subset of goods is just defined as the sum over the goods in the subset of the constituent values for those goods. Okay. So in contrast to the unit demand case, where bidders only wanted one good, here bidders are happy to have all of the goods even. Okay? You keep getting more and more value the more goods that you get. Okay? So, with non-identical goods, this is often an overly simplistic model. This assumes that there's no substitutes. Okay, this assumes that basically your value for getting a good is independent of what else you get. So this is false if there are substitutes, if there are goods that are redundant. That would mean having one reduces your value for having another. It assumes there's no synergies, no complements. Okay, the case where one good all of a sudden makes another good much more valuable. Okay, so again, substitutes would be like two interchangeable licenses, same location, different frequencies, and you don't care which one, and you only want one of them. That would be substitutes. Complements would be if you're trying to piece together regional plans into something that covers a wide range. Then really you want a whole set of nearby licenses. And so having some of them make the others more valuable. That's what we're excluding with additive valuations. Okay? So it's occasionally relevant. But more right now, it's sort of my main motivation here is pedagogical, okay, to increase the complexity gradually, all right? Okay, so let's ask about, the usual direct revelation DSIC implementations, and then let's ask about ascending implementations, okay, just like we did for scenario number 1. So the DSIC direct revelation solution is quite clear. Does anyone want to suggest what it is? So suppose you wanted these 3 properties for scenario number 2. All of you actually know how to do that. Yeah.
It seems like you just do M single item auction.
Right. So additive valuations means I do not care. It means the outcome of other auctions have no influence about my preferences in a particular auction on a particular item. Okay. So my value for getting this good J is independent of what happens in the other goods. My values are additive, the prices paid are additive, so the whole mechanism design problem just separates. Okay? The items decouple. Okay? So really you can just solve each single item auction separately, and we know how to do that. We do that with the Vickrey auction. Is there a question or a comment? Yeah.
Presumably we don't have budgets, right? That we all have to
That's right. That's right. Yeah. Yeah. So no budgets at the moment. Okay, so the DSIC direct revelation solution is very simple. Just run M simultaneous Vickrey Auctions. And we get properties 1, DSIC 2, assuming truthful bid, surplus maximization, and 3. Okay, it's in a polynomial time auction, and it's simple by kind of any definition you might think about. All right. So any questions about that? Again, I'm not giving a formal proof, but it's just, the values separate, the prices separate, so the problems just completely separate. Yeah.
Why does simultaneous matter here?
What else do you have in mind?
Can you run these sequentially?
Yes, you could run them sequentially. Yeah. Yeah. Good point. So maybe I should just say run M separate. M unrelated Vickrey Auctions. Yeah. Other questions? Yeah.
Doing them simultaneously would have the advantage people could learn to collude.
Right. So collusion's a can of worms, which I'm not going to address too much in the class. So that's a good point. I mean, so there's again outside the model reasons you might prefer either simultaneous or sequential. I mean, you could tell stories about why sequential might be better too if you had uncertainty about people's valuations and so forth. But again, that's kind of not the model. The model is just this. I mean, even with collusion, it's a little hard to see how you'd make a clear case that one dominates the other, I think. But yeah. Okay. Other comments, questions? Okay. So, all right. So what about ascending implementation? What's sort of the obvious thing to do here?
Run M separate ascending auctions.
I agree. Completely agree. So here let's actually, here I want to make them simultaneous. Okay, even though, just for an example I'm about to do, I want to think of them as simultaneous. For concreteness. Okay. And so what does that actually mean? So we're going to go ahead and just start all the prices at 0, okay, and increase them like clockwork. We're going to maintain a separate set S sub JT for the bidders that are active at time T on good J. And the jth English auction halts when the number of interested bidders drops to 1. Okay? And at that point, that last remaining bidder gets the good at whatever the most recent price that had demand 2 or bigger was at. Okay? And so the prices sort of go up in lockstep, but the auctions are going to terminate at different iterations depending on exactly how high the second highest bid is. Okay? Is everyone clear on what I mean by run M simultaneous English auctions? Okay. All right, so that seems pretty boring. So what we did for the scenario 1 is we just said everything about the ascending implementation is just as good as the direct revelation one. In particular, the incentive guarantee is just as good. Okay, it's dominant strategy. So we'd like to say the same thing for this. We'd like to say that sincere bidding, defined in the obvious way, you just answer queries honestly on all the auctions. We'd like to say that that's a dominant strategy with parallel English auctions. That seem true? Yeah? Seems true? Okay. Actually, here's a hint. It's not true. So with that clue, does anyone see why?
Why?
Say it again. In what sense? I mean, valuations are additive, right? So what do you mean take a hit? So this is where with this example, we'll start to see where the richness of the action set of indirect auctions kind of rears its ugly head, okay? The point is that there's a lot of things you could do other than sincere bidding, okay? So how can you act in an auction? Okay, well, you can be sincere, okay? You can bid sincerely with respect to your valuation. Here's another thing you could do. You can, in your mind, say, well, let me pretend that my valuation was something other than it is. Okay, I know it's 10, but I'm going to pretend like it's 20, and then I'll bid sincerely as if my valuation was 20. So that's a particular type of deviation. There can also be deviations that are not of this form. Okay? Still more creative deviations. Deviations that are inconsistent with sincere bidding for any valuation. So let's just suppose that there's two bidders and two goods. Suppose bidder 2, let me tell you the values. So bidder 1 has a higher value for both, okay? So bidder 1 has value 3 for good 1, which is higher than bidder 2's value, and similarly for the second good. Okay? So what should be clear is that if both bidders bid sincerely, the first bidder will win both, okay, at prices of 2 and 1. So suppose bidder 2 acts as follows. So in the very first iteration, okay, when bidders are asked, do they want a good, for good 1 and good 2, they're asked, do they want the good still at a price of epsilon? Okay. Bidder 2 is going to monitor bidder 1's response. Okay. I'm going to assume the auction is run such that everybody sees who bids for the good at every iteration. Okay. That's the version of the English auction this example is for. And if a bidder 1 says, yes, I'm happy to have good 1 at a price of epsilon, then it's going to retaliate. Just going to keep bidding on both goods forever. Or, if you like, up to the prices at least say 3 on both. Okay? Even though that's insincere, right? Its value is just 2 and 1 for the two goods, but if it observes bidder 1 bid on good 1 in iteration 1, it's just going to bid way over its valuation. Okay? Else, it's going to play nice. Okay? So this is something bidder 2 can do. This is an action of bidder 2. There's no analog of this in a non-iterative auction. Right? But an iterative auction, where you're asked questions at every round, and you learn information from previous rounds, this is the sort of stuff you can do. Okay? The richer action space enables these kinds of strategies. Okay? Now, what does it mean to be a dominant strategy? So let's think about bidder 1. Right? So I claim that sincere bidding is not a dominant strategy for bidder 1. In particular, it's not a best response to this strategy by bidder 2. Okay? So dominant strategy means no matter what the other person is doing, it's the optimal thing to do. Okay? So what happens if bidder 1 bids sincerely? Well, if bidder 1 bids sincerely, then of course it bids on good 1 at a price of epsilon in iteration 1. Of course it does that. Okay? It's willing to pay 3, so it's going to say, yes, I'm willing to pay epsilon. That triggers bidder 2's retaliation. And as a result, bidder 1 will wind up with neither good. Okay? It'll just get outbid on both goods by bidder 2. Okay? As a direct consequence of it bidding on good 1 at iteration 1. Okay? Sincere bidding gives utility 0. Is there a different thing bidder 1 could do, other than sincere bidding, that would give it utility bigger than 0? Sure, just abandon good 1 immediately. Okay, say you don't want it. Okay? And cut your losses, right? Bidder 2 is going to bid sincerely. So at the very least, bidder 1 will get the second good at a price of 1. It'll get utility 1 overall. Okay? So bidder 2 is going to wind up getting the first good at a price of 0. And bidder 2 is going to wind up, bidder 1 is going to wind up getting the second good at a price of 1. Okay?
And the reason this didn't work in the previous setting is that we couldn't compensate bidder 1. Or bidder 1.
That's right. So basically, I mean, so you can still try to force people out of an English auction, but then they're going to have utility 0.
Right.
And sincere bidding will never get you utility worse than 0.
Right.
So there's no kind of intermediate outcome.
It's still the case here that no one will want to deviate from like a situation where everyone else is bidding truthfully. Like, if
Excellent.
everyone else is bidding truthfully, I'll still want to bid truthfully.
Excellent. That's true. I don't think it's totally obvious, but that's true. It's an exercise. So that's exactly where we're going. So the proposal, which is an excellent proposal, is, well, at least sincere bidding is a best response to other people bidding sincerely. And it's exactly the next step of the lecture. Okay? But it's important to understand we have to change the notion of the incentive guarantee as we pass from direct revelation mechanisms to indirect mechanisms. Okay? We need to tweak what we mean by the best incentive guarantee we can hope for. Given the richness of the action set, dominant strategies is no longer going to be possible. It's no longer appropriate. Of course, this does not mean that ascending auctions are stupid and useless. Of course, this does not mean that no one's ever going to do sincere bidding in a well-designed ascending auction. That's not the point. The point is to refine the definitions so that they say what seems meaningful for indirect auctions. Yeah.
But isn't, if bidder 1 is bidding sincerely here, isn't this crazy grim trigger bidder 2 thing better than bidder 2 bidding sincerely? Because now they have utility instead of 0.
No, if bidder 1 is bidding sincerely.
So-
Oh, yeah.
Yeah. So right. So the grim trigger actually harms bidder 2 quite a bit. Yeah. So bidder 2 falls on its sword when the bluff is called. All right.
So sincerity is an equilibrium?
Exactly. That's what we want to formalize. Sincerity is an equilibrium. So that's what we need to understand. Yeah.
Could we also try, I don't know.
There was a question here first. So.
So in this bidder 2 risks negative utility.
Right.
If bidder 1 assumes, is there a strategy for bidder 2 which guarantees no negative utility but still makes non-sincerity optimal for bidder 1?
Say that again. What was the question again?
So is there an example where bidder 2 takes a strategy which is insincere but will definitely give it non-negative utility, where bidder 1 is incentivized to act insincerely?
I believe so. I'll leave it as an exercise, but I think so. If you play around with the values in this example. Notice here I've made bidder 2 disadvantaged on both goods. But if you played with that property, I think you get what you're talking about. Yeah. Okay. So people have the fantastic intuition. There should be some notion of sincerity being an equilibrium. But it's actually a notion of equilibrium which is different than anything I've talked about so far in these courses. Okay? So we need to pin that down. But the point is definitely to just sort of to understand what is the appropriate analog of DSIC. We think of DSIC as the strongest possible incentive guarantee for direct revelation mechanisms. We now see it's too strong for indirect. So I want to give you, again, the strongest possible, roughly speaking, incentive guarantee for indirect auctions, the appropriate analog of DSIC. Okay? So here's the idea. And so, so basically, this is extremely rare. You almost never see in iterative auctions that have dominant strategies of sincere bidding. Okay, so don't get used to this. This is probably the last time we'll ever see it. Okay. So the idea, as people have sort of been mentioning, so we want the following condition, that whatever people want, so that is whatever their valuations are, and again we think of I only knows VI and doesn't know anyone else's valuations. And for all players I, sincere bidding is optimal for I, provided others bid sincerely. And so I'll do the math in just a second, but what's really important here is that we do not want to use Nash equilibrium as we've been defining it. Nash equilibrium is a full information equilibrium concept. In a full information game, the assumption is that everybody knows everybody's payoffs. So if we play rock, paper, scissors, and I play rock and you play scissors, I know what your payoff is. Your payoff is -1. Okay, if we're in an auction and I see you win something for 10 bucks, I don't know what your utility is because I don't know your valuation. Okay, so we don't want the full information Nash equilibrium concept because I, as a player, do not know what you want. I don't know your private valuation. So what this is trying to say, it's saying, well, let's just assume I know your strategy. Okay, whatever your valuation is, which I don't know, let's assume I do know that you're playing sincerely with respect to it. Okay, so I don't know, I just know your plan. Okay? I don't know your private information. I don't know your actual actions. That should be enough for me to feel confident that bidding sincerely is the best response. Okay? So that's what's subtle here. There's stuff I don't know about you, your valuations. There's stuff I do know about you. Given your valuations, you're bidding sincerely, and that should be enough to conclude a best response. Okay? So in some sense, it's uniform over any valuation you might have, given that you're bidding sincerely. Okay. So here's how we make that precise. So we have action sets for bidders. Okay, and again, in an auction context, this is going to be something like how you answer queries in a given iteration, given the history of everything that's happened so far. So these are big sets, these action sets. Okay. A strategy is, given what you want, how you will act. Okay, so it's a function from your private information, your private valuation, to your action. So example, if you think about it, bidding sincerely as a concept, this is not an action. Okay, bidding sincerely does not type check as an action. It type checks only as a strategy. Right, so the action is actually, do you say yes or no when a bidder when the seller asks you if you want something at 10 bucks. Okay? Your action is just yes or no. Okay, the strategy is to say, well, given what I want, given my valuation, I'll answer yes if and only if my value is at least the price, okay, at least 10 bucks. Okay? So actions are what you do. Strategy says, given what you want, what's the plan of action? What do you actually do? Okay?
So why is the strategy dependent only on my valuation and not on the observed actions of others?
That's all encoded in A sub I. Okay, so the way you should think of A sub I is, it's like a contingency plan for everything that might ever happen, right? So a particular action, a particular element of A sub I is going to be, okay, in round one, so in sincere bid,
so it's not just a yes or no answer to a question.
Well, so in the English auction, I mean, in effect, it is. It's just it's just what information do you base that decision on? So sincere bidding is a particularly simple strategy where when you're given a query, you don't look at how you got there, right? So when you're asked, do you want this item at this price, the only thing you look at is your value for that item and the price. You don't look at what else has happened or how else you've gotten there.
And you're encoding the history into the action.
Yeah, so I'm trying to save you the gory details about what AI actually is, but it's a full contingency plan. Okay, so for example, this crazy strategy for bidder 2 is a single element of A sub 2. Okay, so this is a particular action. Okay, and what it says is basically, the way that you answer these yes/no queries from the auctioneer depends on what the other bidder did in the first iteration. Okay, so all of that is encoded in A sub I. So again, A sub I is super rich, full contingency plan of how you answer queries as a function of everything you know up to that point in the auction. Okay, is that clear?
Nothing about the other bidders?
Well, so that's sort of, I mean, the domain here is v sub I. So this is an excellent point. So, you know, what's interesting here is that you have to commit to an action knowing only what you want and not knowing what other players want. Okay, not knowing other players' valuations. Now, you may sort of learn about other players through their actions, but your strategy is a function purely of your own valuation. And that's exactly what we wanted to capture. Okay, so, right, so sincere bidding, for example, doesn't use information about V minus I. Right. So the assumption in defining strategies this way, we're assuming, I mean, it's really tantamount to assuming that player I knows absolutely nothing about other players' valuations. Okay? Which, again, is very much in the spirit of our dominant strategy implementations, where you said, I don't care what people want. I know this is the right thing to do. So here we're going to say, I don't care what other people want. I only care that they're bidding sincerely, and then I know exactly what to do. That's going to be the analog. Okay, right. So a particularly simple strategy is bidding sincerely. But again, for this to be well defined, it's a function of your valuation. Okay? Whether to answer yes or no, you need to know what your valuation is. Okay, so now consider a strategy profile. Okay, so one of these strategies, one of these functions for each player. This is an ex post Nash equilibrium. E, P, and E, if, and it's basically just encoding this idea here. Okay, so for all I, so whoever you are, whatever your valuation is, whatever other people's valuations are, your strategy is the best response to what everyone else is doing, okay, to other people's actions. Okay. Now, you chose this action independent of V minus I. Okay. So as you vary over all possible V minus I's, all possible things that the other players might want, you're varying over all these various actions that they might be taking. So what this is saying is that your strategy, okay, so what this is saying is your strategy is the best thing for you to do, no matter what other people's valuations are, as long as they play according to these strategies. Okay. So again, as far as how is the player reasoning, this is like the player knowing nothing about V minus I and then almost doing worst case analysis in some sense over V minus I, but knowing or assuming that the other players are playing according to the strategies S minus I. Okay, so it's a uniform best response over the valuations other players might have. So even stronger would be a dominant strategy. So dominant strategy says you're confident that you're doing the optimal thing no matter what other actions people are taking, okay? Whether or not they arise via these announced strategies or not. So a dominant strategy equilibrium would be same thing, but SIVI should be a best response to any actions, A minus I, whether A minus I has the form S minus I, V minus I, or not. Okay? So again, think about bidding sincerely in parallel English auctions as a concrete example. So what we know is not true, we know, oh sorry, this is a dominant strategy equilibrium. Okay. So we know that sincere bidding is not a dominant strategy equilibrium in parallel English auctions. Okay? That's what that example shows. It is not the case that sincere bidding is the best response, whatever the action of the other player. Okay, this is what's false. But we also observed that this weird action by the other player does not arise as sincere bidding with respect to any valuation. Okay, it's some kind of outside-the-box action. We haven't proved this yet, but ex post Nash equilibrium would just say sincere bidding is a best response to any action which arises through sincere bidding with respect to some valuations. Okay? So that's a weaker notion. Okay? It's a uniform best response, but over a smaller set of actions by the others. Not with respect to all actions, just all actions that could ever arise through sincere bidding. Okay? So this is too strong. This is the candidate, and this will be what we adopt as the sort of correct strong incentive guarantee for iterative auctions. Okay? So any questions about that? All right. So as a sort of initial sanity check, initial proof of concepts, it is the case that while in parallel English auctions we do not have a dominant strategy equilibrium, it's sincere bidding, we do have sincere bidding as an ex post Nash equilibrium. Yep. You mean why do we use that word? Why that word? Yeah, the word sort of comes from when you're talking about Bayesian models, right? So if you so let me try to give a short answer. So if there were a prior, then the usual notion of ex post would be after all things are realized, which is sort of like, you know, if something is true ex post, it says whatever the realization. So here again, we're saying, you know, this is the best response, whatever the realization of V minus I. We just didn't have a prior. But if you think about it, you know, if it's for every single V minus I, you don't care if you had a prior or not. It's independent on what the prior was. So it's a good question. So sort of given that there's no distribution here, it's sort of funny, perhaps, verbiage, but that's what we're going to use. Okay. If that didn't make sense, don't worry about it. Okay, so exercise. In scenario 2, meaning additive valuations, non-identical items, sincere bidding, while not a dominant strategy equilibrium, is ex post Nash equilibrium in simultaneous, say for concreteness, English auctions. Okay. The proof is not hard, so I'll leave it to you, but the gist is if everybody else is bidding sincerely, if you think about it, sincere bidding, if you're bidding sincerely, then the different auctions have nothing to do with each other. Okay? Your yes-no answers in one auction will be totally independent of what happens in all the rest, because your valuations are additive. Once you know all the other bidders are not paying attention between the different auctions, then there's nothing you can do. Basically, it reduces to just analyzing each item separately, and we already did the single item analysis. You can't do anything better than just bidding sincerely. Okay? So that's the idea of the proof, but I'll leave the details for you as an exercise. Also, as usual, there's the discretization error, and here you might pick up an epsilon error for each of the M auctions that's being run. So up to the number of goods times the discretization error, but again, as epsilon goes to 0, it's simply an ex post Nash equilibrium. Okay. All right. So a couple senses in which, you know, I want to say that this is a strong incentive guarantee we should be happy with. So I've already motivated why, you know, we can't have even better. We can't have dominant strategy equilibria. But notice it's still pretty powerful to have this, as a bidder, to have this strategy which is guaranteed to be optimal, no matter what the unknown information of the other bidders, just provided they're following some standard natural strategy. So contrast that with a first price auction. Right? So if you're playing in a first price auction with somebody, and suppose I even knew their strategy. Suppose I always knew they were shading their bid by 80%. Okay, and I knew that. I totally want to know their value, right? Because if I know their value, I know their bid is 0.8 times their value, and now I know exactly how to just beat them by plus epsilon. Okay, so you don't have these kind of ex post sort of universal best response properties at all for lots of auctions. Okay, so it's powerful that you don't care, you're agnostic to other people's valuations, assuming only something like sincere bidding. Okay. All right, so in fact, I'm going to define non-standard definition, awesome ascending auctions as just like what we had for direct revelation, except, I should say, one reason I was really excited to teach them about ascending implementations is I have a legitimate excuse in lecture to say that an auction is totally epic. Ex post incentive compatible is literally what these auctions are called in the literature. Okay? So the first thing is the auction should be epic. And then, right, so just like with the direct revelation version, we wanted truthful revelation to lead to good performance, so ideally max surplus. So sincere bidding forms an ex post Nash equilibrium, and assuming that all bidders do bid sincerely, then we get max surplus. You can also obviously thinking about approximate max surplus. And then again, we want some kind of polytime or simplicity kind of constraint. Okay? And so I've given you such an auction for scenario number 2. Okay? And so the question again, the high level goal for the next couple of lectures is how generally can we hope to get awesome ascending auctions in this sense. So I have one sort of final minor point I want to make before the break. But any questions right now? Yeah.
Does making this choice of epsilon a part of the player strategies change anything?
Say it again? Oh, you mean suppose I let the players choose the increment? That's a good question. I'd have to think about it. I mean, I'd have to think about it. Yeah, I'm not sure. All the auctions I was planning on presenting, I was just going to think of epsilon as exogenous. It's just chosen up front. So I don't know. Or how about you let me know, actually. Yeah. Okay, other questions? All right, so I want to do one final point relating sort of the direct revelation version of awesome auctions and the iterative version of awesome auctions, okay? And arguing that one is actually strictly harder to obtain than the other. Okay? Introduce a relationship between the two. All right, so the formal statement here I'll leave as an exercise. It's not hard. But what I want to do here is just sort of outline, what the main point is, sort of why it's an interesting observation. So early last quarter, I told you about something called the revelation principle. Okay? And the point of the revelation principle was to justify why we were kind of focused on these auctions that were direct revelation. Right? So basically where we just asked bidders for their private valuation as opposed to doing something more clever. So the revelation principle is this simulation argument where it basically says, well, give me any mechanism that's guaranteed to have dominant strategies, but there's maybe not direct revelation. Then I'll do a simulation with a direct revelation mechanism, and it'll be just as good. It'll be an equivalent mechanism. It'll be direct revelation. Okay? So what the exercise is going to ask you to do is to apply that exact same simulation argument if you had an ascending auction that was awesome in this sense. Okay? So imagine I gave you an ascending implementation like this one, okay, that was epic, and that had max surplus and so on. The simulation would just be, okay, well, I don't want to bother with this ascending implementation. Let me do a direct revelation version. Let me just ask players for their private valuation. I'll just simulate internally the ascending auction. I'll wait till it halts. That gives me an outcome, and then I'll spit that outcome out. Okay? So that's how you do simulation to go from iterative to direct. And the claim is if you start with an ascending auction that's ex post incentive compatible, you'll get an equivalent mechanism which is actually dominant strategy incentive compatible. Okay? So take an awesome ascending auction, which again is only going to be ex post incentive compatible. Apply the revelation principle. And the claim is what you get is a DSIC direct revelation, and its equivalent. So in particular, if you had these three properties, it will be the case over here. You have DSIC, max surplus, and again, reasonably simple in polynomial time. So what's the point? The point is designing these is at least as difficult, okay, at least as hard to achieve as a designer as designing these. Because whenever you give me an auction with these properties, I have an automatic way to compile it into an auction with these properties. Said another way, a necessary condition for having a good ascending implementation that's ex post and center compatible is to have an equally good direct revelation implementation that's DSIC. So the way this is going to show up is we're going to be striving for these ascending implementations, and we'll always ask a sanity check at the beginning. Well, can we at least solve the easier problem of having a direct revelation DSIC implementation? If the answer is yes, then we can proceed and work harder and get an ascending implementation. If the answer is no, we know to quit. Okay? So that's the relationship between what we studied last quarter and this new sort of awesome ascending auctions concept.